So good evening. Uh, I hope I am audible. Can you please confirm if I am audible?
Good evening, sir.
Yeah.
You are audible.
Thank you. So we'll start with the live session 2 of this course, Digital Electronic Circuit, which is taught by Professor Gautam Saha from IIT Kharagpur, and I'm Anand Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving the week 12 problems. And this will be the last live session, so it will cover the last topic of this course, which is the memory organization and operations. There is some memory cells such as SRAM, DRAM, ROM, PROM, etc. So we'll cover these types of questions, and after that I'll also tell you some of the important questions that we have covered in the previous weeks or from the sequential part, which will be helpful in your final exams also. So without further waiting, let's start with the first question. So the first question states that each cell of a static RAM, so static is inside this SRAM, so this should be static RAM only. Static RAM is SRAM. Cell contains option A says 6 MOS transistors, option B says 4 MOS and 2 capacitors, C says 4 MOS and D says 2 MOS transistors. So we'll study the basic architecture of a SRAM and we'll conclude the answer. So in general, what we use is it is a 60 SRAM, where 60 denotes 6 transistor SRAM. So for now, the correct answer to this question will be option number A. So I'll briefly explain the working of this SRAM to you. So, so this is the circuit of SRAM, as you can see. So we have certain things. So I'll tell you what are these. So M1, you know this is a basic inverter circuit, which is a CMOS inverter, which has a PMOS, then a NMOS connected to it. Here we apply V in and sorry, here we apply VDD and here we get the V out. So this is a basic, nothing but a NOT gate, which is made from a CMOS logic. So here in this circuit, as you can see, M1 and M2 are one of the transistors which are acting as an inverter, and then M3 and M4 are also acting as an inverter. And you can see the input of this M1 M2 inverter is connected to the output of this M3 and 4 inverter. So these transistors are cross coupled. So if I try to make a diagram, so this inverter is made by M1 and M2, and the output of this is connected to the input of M3 and M4, and the output of this is again connected to the input of this transistor. So these are the cross coupled inverters. So if I try to write some of the terms which are associated with it, so M1, M2 and M3, M4 are cross coupled inverters. Then we have M5 and M6, which we call as excess transistors, which will decide what bit it will hold, read, or write. And there are two nodes you can see, one is Q and one is Q bar. So we know that if there is certain input to an inverter, it will always give a Q bar. So it is made like that. So this Q and Q bar are known as the storage nodes. So as I told you, this is a cross coupled inverter, so we can make it something like that. So we have a M5 here, we have a M6 here, we have a word line here, then this is bit line, complement, and this is bit line. So let me try to explain you some of the operations. So it has three operations basically. One is hold, one is read, and one is write. So if I talk about the hold operation, in hold operation there is no read and write. And in the hold operation, what we do, we just ground the word line. So once this is at ground, what happens is this transistor does not conduct, and it just hold whatever is inside this cross coupled inverter. So as you can see, once we hold or once we ground these lines, the only circuit left with us is this. So if we apply a 1 here, it will give a 0, and it will apply a 1 here. So it will just hold the value. It will not operate, or it will not flip the any input or output. So this is how the hold operation works. Next operation which it gives is the read operation. So in read, what we do is, first let's suppose that we want to read q as 1. So q bar will be 0. So this will be 1. This one will be 0. So what we do is, before the reading operation, what we make is DL complement, and this is the bit line, and the bit line we make them as VDD. So we precharge them as VDD. Why we do that? Because we want these transistors to work now. So if we precharge this baseline complement and baseline is VDD, so these transistors M5 and M6 will get turned on. And once they will get turned on, we will have the access to this q and q bar state. So once they will turn on, this q will get passed to the second inverter, and we will get a certain output which is 0. So this is how. And also, yeah, word line should also be VDD. So once they will get turned on, we'll certainly read that bit in the read operation. So I'm covering quite the basic of it. You can refer to the lecture notes also for the more details. And there is the last operation, which is write operation. So write operation is nothing but, in this also we make this word line as VDD, and we make this baseline bar as VDD, and this baseline is ground. And writing operation means we just flip the states, because we want to write certain states. So whatever state it will be, it will flip the states to the next stage. So yeah, these are the basic components of a write operation. And as you can see, if I make this baseline as 0, sorry, bit line as 0, and this will be 1, and we always have this as VDD. So once this will be VDD and this will be VDD, this M5 will get turned on, and we'll have the access to this transistor, which is the inverter of M1 and M2. So again, we can suppose that Q is 1 and Q bar is 0. So once we have a 0 here, this inverter will work, and it will get a high of, since we have this inverter on, what it will do, since we have a Q bar as 0, this inverter will give the output as 1. So this is how we are flipping the states. So there are two phases involved in this. First, what is happening is Q is tending to 0 as we are applying this VDD. So this Q is tending to 0. Since we have a 0 here, a VDD here. So as Q tends to 0, we know this inverter will work. Since this M5 is turned on, then Q bar will tends to 1. And this is how we are flipping the bits. So this is a basic of SRAM, which is a 60 SRAM. So the correct answer to this question was 6 MOS transistors. If you have any doubt, you can write in the chat box. Uh, okay, so let's go to the next question also, because it is a similar type of question. It talks about DRAM. So it is again asking the minimum number of transistors required to make a DRAM. So now a DRAM is of two types. One is a three transistor DRAM, and one is a 1T1 capacitor. This is a one transistor and one capacitor DRAM. So the minimum number of transistors from which we can make a DRAM is one only. So I'll explain the circuit of these also, quite basic part. So a three terminal DRAMs look something like this. We have a write word line, we have a read word line, we have two bit
Sir,
lines.
uh, we
Yeah,
can use the capacitor with one transistor, no?
we can use what?
Sir, one transistor and one capacitor can make a DRAM.
Yes, exactly. So wait.
Okay, sir.
So I guess you are saying something like this, uh, right? So it this capacitor will store whatever there will be the input, right?
Yes, sir.
Yeah. So this is a similar circuit. So this circuit, it is a one term transistor and one capacitor circuit. So you need to just focus on this. This extra are the word line and bit lines, whatever input we will apply. So that is why I have marked the answer as one only. So minimum number of transistors to make a dynamic RAM is one only. That is what you are saying. One transistor and one capacitor, which is this circuit, the right one. Is it fine? I'll explain the working of it, but is it fine?
Yes, sir.
Yeah. So if we talk about first this three terminal DRAM, three transistor DRAM. So we have again two operations. One is write and one is read. So write operation is quite simple. So what we do is whatever we want to write, we just put the value of that particular bit on this baseline one or the bit line one. So you can see if you let's suppose if I want to write, so I'll make this as one, and we know if this capacitor is initially charged or discharged, what it will do is it will get discharged or it will get charged accordingly. So if it was initially at 0 volt, it will get charged to the VDD once we apply a high amount of voltage. And once it let's suppose it was at VDD and we applied a 0 here, so it will get discharged like that. So this is how we'll just write. So it is quite a simple operation. It just depend upon this CS. It will get charged or it will get discharged according to the input applied. If we talk about the read operation is in this what we do is we pre-charge this baseline
Please
too.
explain read operation. I have
Yeah,
forgotten.
sure. Which operation, read or write?
Sir, both these.
Okay, so I'll explain the right one again. So for right one, what we do is whatever input we want to write in this three terminal, we just apply it to the baseline one, BL1 or the bit line one. So let's suppose I want a high input. So once I have applied this high input and we have this right line as VDD. So this transistor will be on, right? Because it has a VDD at gate and source. So what will happen is it will conduct. So whatever the input applied, I have applied here, it will get charged here. So I have written this VDD in the CS. So this is writing one. Similarly, if I say for let's suppose 0, if you want to write. So there is a VDD, there is a 0. So now the transistor will not conduct since the drain voltage is at 0. So what will happen? This capacitor will get discharged to the ground. This is how now the it will change to 0. So this is how we will write a 0 here. So this was a write operation. So now I was talking about the read operation. So in read operation, what happens is we pre-charge this BL2, which is the bit line 2 to VDD, and we on this read write line now. So you can see this read write line is connected to this transistor here, and we have this baseline as here. So this is a basic inverter circuit. If you can refer to the slides, whatever X is there, the invert of this will come here. Let's suppose X bar if I'm plotting. So based on the value of this X, we tune. Let's suppose we have a high X. We have given a 0 here or a VDD here. So we have X equals to 1. Once this X equals to 1, this M2 will get turned on because we have applied a certain amount of voltage which will turn this M2 on. So when this M2 is on, we'll get an inverted output of X bar here, which is nothing but 0. So this is how it will read. Initially I have applied a 0 which is giving this X as 1, and then ultimately I'm getting the my output as 0, which is reading the output. Similarly, the same can be done for VDD also. So I don't want to cover much more depth of this DRAM SRAM because this topic is purely theoretical. So you can refer to the lecture notes also for this topic. And I'll explain this basic one terminal, one capacitor. So again, for this writing operation, we just do word line to VDD, and what will happen? This will get VDD. So now you know this transistor will be in saturation. So once this transistor will conduct, this VDD will come across this capacitor, and this capacitor will get charged to VDD. So this is how we have written 1. Same is the case with 0. This transistor will not conduct, and now this capacitor will get discharged through this path because here is a VDD. A MOS is a symmetrical device. We can interchange this drain and source. So this is was again the basic operation of writing, and read operation follows the same as we have done here. It depends upon what input we have applied. So the main motive is you should know that what are the minimum number of transistors, or how a DRAM operates in its two types of operation, which are read and write. And again, it was the SRAM. So I tried to explain in brief that how these both of these circuits have worked. Uh, if you have any doubt, you can ask now. Then we'll go to more problem-based questions which are given in your assignments.
Sir, 3T DRAM, can you please explain one more time? 3T DRAM.
Okay. So, so there is two things: write, read. In write, this write word line was set to 1. So 1 means VDD. So you can see this VDD will come here. Let me use some different thing. It is not visible. So this VDD will come here. This will always be VDD during the write operation. So suppose now I want to write 1. So what I will do, I will give this bit line to 1. 1 means VDD. So here it will be VDD, right? So VDD and VDD is here. This transistor will conduct because it has a certain amount of voltage required at drain and gate. So once it will conduct, it will act something like a short circuit ideally. So whatever VDD it will be, it will get charged here. Is it clear, this part? So this is how we are writing 1. So now the same case with 0. Once it will be 0, we already have a VDD here. So now the path will be in the opposite side. So this VDD will get converted to 0. So this is how we have written 0. Is this clear now?
Yes, sir.
And this circuit, whatever I am putting in a circle, this acts as an inverter. So whatever the value of x, it gives the invert value of x here. So let's suppose x was 1. You know, when x was 1, this transistor will get turned on because we have a certain gate voltage that it will get turned on. So now we have a voltage here, and we what was this? So whatever we want to read or write, so let's suppose we want to read 1. So we'll have a 1 here, and we have a certain voltage here. So it will give a 0 voltage because it was 0 here, right?
Okay, sir.
Yeah. So this is how the read operation works. Similarly with the 0 part also. So these types of question, theoretical question won't appear, I guess, in your exams, but they will be more circuitry based. So I'll let you know what types of question will come in the upcoming questions.
Yes, sir. We can discuss all important questions of the previous weeks because
Yeah,
today is the last week.
yeah. So I have added those questions which I feel is important in the last
Okay,
section
sir.
of
Okay,
this
sir.
lecture. Yeah. So I'll not solve them, but I'll just tell that what I feel is important and what you can focus on more. So let's go with the first proper question of this SRAM DRAM. So we know that this is a basic circuit of a control logic input. So for this question, you just need to know about the truth table of this. So if you don't remember, I'll make it. So what we have is we have truth table in which we have a CS, we have a read by write, then we have write and read. So there are only four possible cases in this. So using this truth table only, you can tell you the answer of this particular question. So it says when both of them are there, then only it will write, and it will read when CS is 0 and this will be 1. So this is a truth table of the particular question. So it says a control logic input CS bar is 1. So CS bar is 1 means CS is 0. and the next thing is R by W complement is 1. So if I try to see it through the truth table, there is only one case in which CS is 0 and R is 1. So you see only read operation is happening at this particular instant. So the question says that which operation will take place. So for this particular case, when CS bar is 1 and read by write complement is 1, only read operation takes place. So the correct answer to this problem is option A.
This is the shortcut trick because we have OE another table CS OE reader write and write
Yes,
then
yes,
read.
yes, exactly. So this is the shortcut. If you are just getting these two values, so you can apply this shortcut. You can use this truth table and just directly get the answer, because the
Yes.
question paper might be lengthy, so you should know some tricks.
Okay, sir.
Yeah.
Thank you.
So let's proceed to the next question now. So it says how many data input and address input lines are required for a 128K cross 16 memory unit. So we know the general representation is nothing but 2 to the power p into n memory unit. So I'll just, let's suppose we have a certain data inputs, we have certain address inputs, which are number as p, which I have marked here, and we have n data inputs, and m here represents the number of locations, which is not asked there, but you should know about it. So we directly have this 2 to the power p as m, which is 2 to the power p is 10, sorry, it is what, 128K, and 128 is nothing but 2 7, and 1K is nothing but 2 to the power 10. 2 to the power 10 is 1024. So 1K is the same. So it was not 2p, it was 2 power p. So you can just add the powers. So p will be nothing but 70. Now the next question asks is, first was the data input. So the data input was nothing but n data inputs. Okay, so now we'll calculate the data input. So general data input says this m cross n is nothing but 128A into 16. So if we try to cover them or compare them, n will be directly 16. So the question says first the data input and then the address input. So address input lines were 17 and the data input was 16. So the answer is D. Yeah. I hope it is clear. If you have any doubt, you can ask. We shall cover the next question in 2 minutes.
It's clear, sir.
Okay, okay. We shall start the next question in 2 minutes. Okay, so let's proceed with the next problem now. So we have a 1 mega cross 4 memory, and we need to find the number of 64 kilo cross 4 memory circuits required to make the same. So this is quite simple. So we have 1 mega cross 4, and we have to make it using 64k cross 4. So we know 1 mega is nothing but 2 to the power 10 into k. So I'll just write the same here. So it will be 2 to the power 10 into k, and then 64 is nothing but 2 to the power 6 k into 4. So we'll just divide them. What it will give is, it will give 1024 divided by 64, which will be nothing but 16. So this is similar to a mux. Then we do this division 16 by 4 and then 4 by 4 and go on. So we will require 1664 cross, sorry, 64k cross 4 memory circuit to realize 1 mega cross 4 memory unit. So the correct answer to this question is 16. If you have any doubt, you can ask. Start the next question in 2 minutes. Maybe you can try the next question by yourself because it is quite easy. It is a PLA question, so you can try. If it is not visible, let me make it clear. The connections. So one connection is here, one is here. Yeah. Now you can try this question. I'll give you 5 minutes for the same. Any answer? Okay, so let me try to do it. So these are the AND gates. These are PALA. So I'll write the output of AND gates first. So for the first AND gate, we know that these and these. So this is A bar, this is A, this is B bar, this is B, then this is C bar, this is C. So the output of first AND gate will be A bar, C bar. Second will be we have A, B bar, and then C bar. Third will be we have a B bar and then a C bar. Fourth it will be A and then C bar. Is this clear? Okay. Second is ABC. This is A. This is B. Okay, sorry. So this is wrong. I marked few is wrong. Yeah. So now it is fine. And then this was C. Is it clear?
Yes, sir.
So now we'll write the output of the OR gates. So OR gates is second plus fourth. So I'll just add the bits. So for the second OR gate, the output is second plus fourth, which is ABC plus AC. And for the first, it is 1 plus second plus C. So it is A bar C bar plus ABC plus B bar C bar. Now we know that for an XOR gate, which is a final F1 and F2, if we add a 1 and if we have a X here, so it acts as an inverter. The output will be X bar. How it is coming? So let's suppose we are XORing. So it is X into 1 bar plus X bar into 1. So it will give X bar because this will be 0. And for if you apply a 0 here instead of 1, it acts as a buffer. It is nothing but X into 0 bar plus X bar into 0. It is X. So you can see F2 is using 0 and F1 is using 1. Okay. Do you have any doubts?
No, sir. Answer is option A.
Okay, fine. Yeah, we shall check if it is correct or not.
Okay, sir.
Yeah. So we'll have the X bar is coming from which? Yeah, F1. So F1 will be nothing but this term bar which is coming from first. This is F1. So second, yeah. So F1 will be ABC plus AC whole bar. And if you try to simplify it, if we take AC common, it will be B plus 1 and B plus 1 will be 1 only. So we have AC whole complement, which will be A complement plus C complement. So since the options are in main terms, we need to make the KMF or we need to expand the same. So we shall do it something like that. Let's suppose. So it is A bar B, A B bar plus. So now I'll write C plus C bar. Then I'll write for this. It is A B bar C plus A B bar C bar. Then we'll write for this A B C bar plus A bar B C bar. And then for the last term, which is A B bar C bar, and one is A bar B bar C bar. We'll write the corresponding min term. So this is 0. First of all, let's see if it's something is getting repeated. So this is getting repeated, this is getting repeated, and then I guess everything is fine. So this is a 0, this is 100 which is 4, this is 101 which is 5. So this is 010 which is 2, this is 6, and this is 3. So let's see, it is 0, 1, 2, 3, 4, 6. 0, okay, I've written, I guess this one is wrong. 0, 2, 6, 3, 4. Okay, 1 is not matching. Fine. A bar, C bar, so. Okay, so this was B bar, sorry. This was A bar, B bar. So I've written this is A bar and this is A bar. So this will be 1 and this will again be 0. So it is getting repeated. So we now have 0, 1, 2, 3, 4, 6. So F1 is nothing but minterm 0, 1, 2, 3, 4, 6, which is in only in option number A. So we can check for F2 also. So F2 will be the buffer of this. So F2 will be directly whatever the input is applied to it. So F2 will be not written it, but it will be this. F2 will be this. So we can expand this. It is easy. ABC plus A bar C bar plus B bar C bar. F is plus B bar C bar. So I'll write A plus A bar here and B plus B bar here. So one term is this ABC, one term is A bar B C bar, one is A bar B bar C bar, and one is this is getting repeated. So last term will be A bar B bar C bar. So this will be 7, this will be 0 1 0, this will be 1, this will be 0 1, sorry, this will be 0 1 0, so it will be 2, and this will be 4. So what is this? 10247. And where is the bar here? Okay, I have written it. This is the one. Let me rewrite it. One is ABC, one is A bar B C bar, one is A bar B bar C bar, and last is A B bar C bar. So this is 4, this is 0, this is 2, and this is 7. So 0247. Yeah, so which is option number A only. I hope it is clear. So let's proceed to the next question now. So it says which of the following statements is or are true. So this is quite a easier question. This topic is more theoretical, so it will not have certain brainstorming problems. So the first option says the main memory of a computer system must be non-volatile. So we know the main memory is RAM, which is volatile only. This is wrong. The data memory can be used built either ROM or RAM. It is wrong. We need both ROM and RAM to do that. It says the write enable time is the time between the placement of stable address and availability. So it is not that. The write enable time is the minimum time required to write. It is not the placement of a stable and the availability of the stable address. And the last option says that SRAM using CMOS uses cross-coupled inverters. So this was the question number 1, which already we have covered. So this is the correct statement that for a basic memory cell, we require two cross-coupled inverters, two cross-coupled inverters with excess transistors, which are M5 and M6. So the correct option is option D. So I hope it is clear. So we can proceed to the next now. Okay, so it says that we are using a linear addressing in memory IC, and the IC has a memory of 1024 cross 4 bits. Then we need to redesign the IC to have a matrix addressing. So we have two types of addressing. One is linear in the question and one is matrix. The total number of input pins to the address decoder for both linear and matrix addressing are, so we'll first calculate for the linear. So I'll write certain formulas that we require in this. So for linear addressing, number of inputs required to the address decoder, it is nothing but log 2 m, and m is nothing but this 1024, which is log 2, which is 10. So for linear we require 10, and similarly for matrix there is a formula. We have number of inputs to the address decoder. First of all, it will be addressed by 2, linear whatever we are getting, and we have the same as with columns, which will be same as the row. So the total requirement will be the addition of the same. It will be 10. So the correct option to this is option B. We shall start the next question in 2 minutes. Okay, so let's proceed with the next question. So it says we need to choose a suitable memory IC, and we have only IC2114 and IC2115. So you can refer to the next lecture notes again. So IC2114 is a word organized IC, and it uses common inputs. Then IC2115 is bit organized and it uses separate IO memory types. So the question now says your requirement is for a word organized and separate IO. So for word organization, what we require is IC2114, and for separate IO, we require IC2115. And we have only a single IC, so it is not like it will happen from a single IC only. So the correct answer is none of them will be suitable for this operation since we require both of them together. So only one IC will not do the operation given in the question. I hope it is clear. Uh, we shall start this question in 1 minute. So this is a general uh, DRAM question, which is 3T DRAM. So we have already covered that this Y depends upon this V, and for it says you need to first write a signal 1. So for writing a signal 1, we need to make this W as VDD, which is high, and for writing this, we need to make this input as high. The read also we need to do high, and once we have both of them as higher, so we will receive a V high, and we'll receive a input which is inverted, which is low. So according to the question, W will be high, then R should be high, and then this Y should be low. So the correct answer to this question is high, and then low. So we have already got a similar type of question. You can try this one now. I can give you 2 minutes. Okay, so we shall try the same now. So we have a IC2114, which is 1024 cross 4 bits memory chip. Then we have a IC74201, which is 256 cross 1 bit memory chip. So how many ICs are required of 74201? So we can write it directly for this IC2114. Okay, give me a moment. So so we know that we have a 1024. So we have log 2 1024. That is the number of address lines. So we require 10 address line for this. And for IC 74201, sorry, this was 2114. We require 256, and which is 8 address lines. So for expansion, we know that we need this 1024 divided by 256, which is we done in the last questions, which is 4 ICs of 7420. Now it says for both address and data range expansion. So for every expansion that we have done for the 4 IC of 70241, there will be a data range expansion also. So we further need for every IC, we further need for 74201 ICs. So the total IC we can write now directly as 4, and for every IC we require extra 4. So the answer will be 16, which is option C. I hope it is clear.
Yes, sir.
Okay. So we shall proceed to the next question now. So it says which of the following statements are true. Okay. So it says that EEPROM uses UV light through quartz window to erase. So this is not the statement for EEPROM. This is for EPROM, which is electrically programmable. So double EPROM is electrically. It uses electrical signals instead of the UV radiations. So this statement is false. Now it says PLA and is fixed and or is programmable. So this is also wrong. It because both and or are programmable. So in PAL, or is fixed and is programmable. So this is correct. This is how a PAL works. We have a fixed or gate and we have a programmable and. And the last option says DRAM. Yeah, so DRAM has a higher packing density as compared to SRAM. So this is also correct. So the correct answers are only 3 and 4. So as you can see, this topic is quite theoretical and does not require much conceptual knowledge. We can proceed to the next question, which are also theoretical. So it says which of the following statement is true again. So in RAM, we know the access time is independent upon the location. So independent is option number B. And then it says in a sequential access memory, it is dependent. So this is also wrong. So this is also wrong. So these are theoretical questions only. So you need to know the basic knowledge of RAM and ROM. You can refer to the lecture slides also. So let's proceed with the next question. It says SRAM memories offers. So SRAM is a memory which is stored near the computational unit of the system. So it offers, the main objective is to give high speed. It is expensive It has a lesser density as compared to DRAM, and it also consumes high power. So if it says high density, so it does not offer high density. It does not offer high low cost also, and it is having higher power. So the correct answer is only option C. Okay. Now you can try this one. So if you can do the same, I can give you 2 minutes for that. Any answer? Okay, so let me try to solve it. So we have already done this. We have a memory unit given 1024 cross 64. So we can write it something like 2 to the power m cross n, or 2 to the power k cross n, where 2 to the power k is the number of words, n is the number of bits per word, and k is the number of address lines which is asked in the question. So if we can compare directly, 2 to the power k is nothing but 1024, which will give 2 to the power k as 2 to the power 10 and k as 10, which is the number of address line required for the given memory units. The correct answer is option C. Any doubts? If you don't have any doubts, please try to solve this question. So we have already done this type of question just now. I can give you 5 minutes. Answer. Okay, so let me try to solve this. This is A bar, this is A, this is B bar B, and C bar C. So again, this output for the, let's suppose this is 1, 2, 3, and 4. This is 1, 2, and 3. So for the AND operations, the output is, for first it is uh, this B bar and then C bar. Second it is B bar into, sorry, so this will give 0. Third it is B C bar. Fourth is A, then B, then C. Now the corresponding output of the OR gates will be first and third, A bar B C bar plus B bar C bar. Second will be second and fourth, so 0 plus this is ABC, and third is nothing but 1 second and fourth, so B bar C bar 0, and fourth is ABC. Second is ABC, sorry, first, second, and fourth. Yeah, which are correspondingly, this is F1, this is F2, and this is F3. So you can check the options. F1 is AB, this is F1, this is F2. Yeah, so the correct option is option B. So now this is all for now. So now I'll tell you some of the important questions from the previous week, and we will we can finish the lecture in maybe 10 to 15 minutes. So you can wait for 2 minutes, then I'll try to tell you the important questions. Okay, so let me try to give you a brief overview of the previous weeks also. So if I talk about week 11, which is the last week, which was the last week, so there were few important topics, and what I found the most important one was these type of question. This is a SAR ADC question in which we have covered that what will be the output pulse after this is end of the third clock. There were a certain question in my lecture which was at the start of fifth clock and something like that. So these type of questions are quite important because it requires some calculations and your conceptual knowledge is also required in these. So from the week 11, the most important questions were these SAR ADC's question and this D to A converters which are given for a certain full scale range. So we have this, if you remember, full scale upon 2 to the power n minus 1, which is the resolution. So these types of questions are also important which requires a value of n. So this n bit operations option and this RADC's options, questions are quite important from week 11 as far as I am concerned. I'm not sure about what will come in your examination, but I'm talking from my perspective that what can be the important topics. You should know how a SAR ADC works. You should know the basics of flash ADC also. Like it has 2 to the power n minus 1 comparators and how it is making a circuit and how it is working. Then you have certain DAX also, such as R2R ladder. You should know how a circuit works for R2R ladder, and there is one which is weight DAC or binary weight DAC. You should know what is the difference in these. The resolution of this is nothing but V upon 2 power n, and this is V reference upon power n minus 1. So these are the basic differences in these DACs. Then you had topics from week 10 now. So this was all about week 11, which was a quite important topics. In week 10, we had this type of conversion tables. We have this row elimination method that covers certain subsets. We had, uh, I'm forgetting the name, but yeah, there are certain state tables. So you know the most important thing you should know is state transition diagram, how to make a diagram. Because if you don't know it, you might face a lot of problems. Because once you have a state transition diagram given, you are allowed to make a truth table for the same, which is given as current state, present state, then input, then next state, then output, etc. So you should have the basic knowledge of this state transition diagram covered as much as you can, because these are quite important questions. This will also help in solving this Mealy and Murray machine problems, because you will get to know that whatever is the state or output, if it is dependent upon only input or the state also, so then you can correspondingly classify which machine is it, what is the sequence. So one more important topic in that lecture was sequence detector. You have a certain state diagram given and you need to calculate what is the sequence it is detecting, so you should know how it can get detected, which is sometimes something like this. You should know how to generate or how to get a sequence out of this, and from the state transition diagram you should know how to calculate or how to realize the boolean expressions. Sorry, this will check your conceptual knowledge, how you can how you have the ability to solve the problem. So you should know from a state transition diagram how you can approach towards solving a boolean expression for a given flip flop. So in this question, let's suppose D is given, so you should know that how to approach. You should know what is input and what is output in this, and these are the states. This is the input, this is the output, and how they are changing. So you should know or everything about it. From the diagram also you should tell that if it is a Mealy machine or if it is a Murray machine. So as you can see, it is only state dependent. So it is a Murray machine only. Then one more important concept, I guess this is from week 9, which includes the synchronous and asynchronous counters. You should know from a circuit directly that which is the synchronous counter, which is the asynchronous counter correspondingly. Synchronous counters are the ones which all the clocks are shorted, or all the flip flops are working at the same instant or the same cycle. And asynchronous in this clock depend is dependent on the previous input or the previous output. You can say you should know how to realize asynchronous type of question, because these are quite tedious to solve, because this requires more conceptual and fundamental knowledge. Synchronous questions are quite easier, and in this you have main two circuits. One is this Johnson counter, one is this ring counter. And asynchronous we have certain circuits, so you need to know how to solve them. Like this is a, you can directly see that this is a asynchronous counter, so they are trying to make you realize the expressions here. Sorry, this is a synchronous one. All the clocks are shorted, you can see. Sorry, it is asynchronous only. They are not shorted, they are dependent upon the previous output. So you should know how to approach these types of question to find the certain logic which is given in the question. So this is from week 9, 10, 11, most of it. Then from previous weeks, one is this LFSR, which is quite the important topics. You remember there was a four state, and we just make an XOR connection with some state and go inside, something like that. It is PQRS, something like that. You should know how to approach a LFSR question also, how to write this polynomial representation and all of that, because they can ask you for the generation of pseudo random sequence, and they can ask you for the period of that particular sequence. Apart from that, these are the general LFSR questions again. There are four types of register, serial in, serial out, parallel in, parallel out, then serial in, parallel out, and then parallel in, serial out. So most popular type of question will always come from serial in, parallel out, which is these types of questions. So they will ask that after how many cycles the output will get to the same as given in the question, and then uh, so yeah, the most popular questions will come from this serial in, parallel out only. They can even ask that after how many circles this 1 0 1 1 0 0 will become 1 0 1 0. So you need to check for the whole cycle when it is getting that 1 0 1 0. They can ask that after four clock pulses, what is the output and to the this shift register. So these are the types of questions from the sequential part. And then from the week 7, which was the starting of this course, the most important topic was flip flop conversions. You should know how to convert a certain flip flop into another, because it is the most important and the basic fundamental knowledge that you should have. You should you should make any AB flip flop from a given JK, let's suppose flip flop, or a D flip flop, or a T flip flop, or a SR also. So you should know the procedure, that what are the 5 points you should remember, which have already been taught in the previous live sessions also. So you can look through the videos also. Uh, so there is a channel on the YouTube, if you want to see all the week 12 videos, so you can search it. I have uploaded all my videos here, so you can go and check the videos here. By typing this, you can get the channel, and it will have all the week videos by today. It already have 11 videos of the previous 11 weeks, so this video will also get uploaded by today only. And from the combinational part, if I talk about, so this was all about sequential part, which is the most important part, to be honest, of this course. From the combinational, you should be able to solve the problem of propagation delay. There was a question in our assignment which consisted of two mugs, and they were asking that there is a certain gate here, there is a certain gate here. So what is the maximum propagation delay that you can get? So you should know how a mux work, when is the select line high, so which path it will cover, and something like that. So you should be aware of the fundamentals of mux, and propagation delay is quite an important topic from the combinational part
So
of the course.
the total number of questions in final exam should be 75 or 100.
See, the question paper format will be given to you by NPTEL only. We also don't know the exact number of questions, but they will provide you a certain format that these much question will come. I guess today they have released the hall ticket also, and something like that. So they
Yes,
will
sir. All
also,
ticket already released, but the pattern
yeah.
of the question they will say it should be MCQ, but how many questions are there? I don't know.
So maybe you can uh, directly email to the NPTEL team. They will like solve your query regarding the same. They will tell you that what is the pattern and whatever is the number of questions that will come in your exam. So they will let you know if it is a feasible question.
Okay, sir.
Yeah, and then from the combinational logic, K maps are important. If you don't know how to make a K map, you will get stuck in a lot of problems. So do remember how to make a K map. Then uh, there was Boolean algebra also. You should know the basics of Boolean algebra. There are theorems such that a plus a power b is nothing but a plus b. So there are certain theorems also that you need to cover. So let me try to go to the syllabus. Yeah. So the initial parts were covered by diodes and circuits. So this was quite basic. I don't know if it is much concern, but yeah, week two to week five there were certain topics such as adder, subtractor. You can see they can use a highlighter. So so this is quite important from this perspective. Then there were theorems, certain theorems which is used. Then there was K map, POSSOP, etc. Then minimization you have already covered, and it is quite easy also. There was some hazard also, which is quite basic. It was a topic of like 10 minutes to cover. Then this is most important, mux demux. So this week is quite important. Week 4 you can go through again. Then 5 again include this Boolean algebra, which is already a part of above lectures also. So don't waste much time on it. Then this magnitude comparator is one circuit, and there are detecting ports also, which I have covered in the week 6 lecture. And then the most important, yeah, week 6 I have already explained you some of the important questions, which are the flip flops and the conversions. How can you use a flip flop to convert it into another flip flop? Then week 8 includes the synchronous registers, which I have already covered, which are the shift registers. Johnson ring counter are the most important ones. Then sequence generation. Then week 9 is again asynchronous counters. We have covered a lot of questions for the same. And in week 10 also we have, yeah, so this is Mealy and Murray model are quite important because it covers state transition diagrams. Then ASM chart also is a good topic to cover. And in the last week we have covered this R2R ladder and binary weight DEX. Then we have this, what we have, this SAR ADCs and etc., which are not written here, I guess. So it says analog to digital converter, so it includes that part of SAR ADC. So you should go through it. And for today's lecture, you can see that today was more theoretical part. So you should not bother much about it. You should just read the part, and because no conceptual question will come from this part, I guess there were only few which are to calculate the address line, bit lines, etc. You should go through that how this 60 SRAM works, how a 1T 1C SRAM DRAM works, and all of that. And there are few questions only. So this was a shortcut. There was OE etc. also, which I have not written. And then again they all were similar only, like tell me the number of address line, number of inputs, number of locations, etc. And these types of questions are quite important from today's topic. So these were the most important one, I will say, which requires this PAL PLA. So they will ask you to realize a particular circuits, what is F1 F2, and yeah, then all were theoretical only. You should have certain knowledge what is IC74. So in week 11 also there was a DAC, which is DAC 0808. So you should not get worried about the by the name only. You should know that it is just a 8-bit DAC and nothing. So don't get worried about the big names. You just know the concept and the fundamentals, and you will score good marks. So yeah, I guess this is all for now. So if you have any other query, you can ask, and else we can wrap up this session or for this course, and maybe we can meet in some new course in the next semester. Do you have any query?
This
Sir,
session
if
is
you have
also
any
uploaded.
doubt,
Sorry, one by one.
These questions are there in the NPTEL course. They are uploaded
Which
on the drive, Google Drive. Please, can you share the link?
so it is not on the drive. You can check the videos directly. So you can type. Maybe I can help you. Sorry. In the YouTube, you can go and type my name or any other TA's name. Also, it will appear. So there is a channel which
sir, is there any available of these materials in the PDF form in the drive?
yes. So that will be provided by NPTEL only. So they might have provided you some link, right?
Sir, for this lecture, do you have this?
For this particular lecture, you are saying?
Yes, sir.
So you have the PDF for the till the week 11 lecture, right?
Yes, sir.
So yeah, so this will be given to you also, as they have given for the previous week. So this will be given to you in that drive link also.
But sir, presently, if you want to repeat the lecture again, then I have to visit to your YouTube channel.
Yeah, so I'll first upload the video and they will also upload it in the drive. So I guess it is a matter of say 1 day, or I don't know when is your exam.
Sir, it's 29th.
29.
So yeah, so you will get it by before that, like maybe in 1 or 2 days you will get the PDF form, and by today you will get the video of the same.
Okay, sir.
Yeah.
Thank you.
Thank you, sir.
Okay. Any other doubts?
No, sir.
Okay, then we can wrap up this course. And all the best for your exams. Hope you will do well. Best of luck.
Thank you, sir.
Thank you.